Start with the square root of 2, a number just past 1.4, and stack it on top of itself. The square root of 2 raised the square root of 2 raised the square root of 2, and keep going upward without stopping. At first, it looks hopeless. Each new floor makes the tower taller, and a tower that never stops getting taller sounds like it should race off to infinity. But watch the actual value as the floors pile up. One floor gives about 1.41, 2 floors 1.63, then 1.76, 1.84, 1.9. The number is still climbing, but each step forward is smaller than the last. It is closing in on something. It settles, exactly on 2, an infinite staircase of square roots of 2, and the whole thing weighs exactly 2. Not near 2, not 2-ish. 2 on the nose. That is strange enough on its own, but the real question is the one hiding behind it. This trick worked for the square root of 2. The moment you try it with a slightly bigger number, everything changes, and there is a single sharp value where the whole idea breaks. Leonhard Euler found exactly where. First, let us be precise about what we are even building, because it has a name and a clean rule. You already know the ladder of operations. Adding is repeated counting. Multiplying is repeated adding. 3 times 4 is 4, added to itself 3 times. Raising to a power is repeated multiplying. 3 to the 4th is 4 threes, multiplied together. Each operation is just the one before it, done over and over. There is an obvious next rung on that ladder, and it is the one almost nobody teaches. Repeated powers. You take a number and raise it to itself, again and again, building a tower of exponents. That 4th operation is called tetration, and an infinitely tall tower is what we were just stacking. The rule for reading a tower matters, so fix it now. A tower is always evaluated from the top down. You start at the very top floor and work your way to the ground. For a finite tower, that is just careful bookkeeping. For an infinite tower, there is no top floor to start from, so instead, we grow it from the bottom, one floor at a time, and ask what value the whole structure approaches. Take the base, raise the base to that, raise the base to that, and repeat. If those running values home in on a single number, the tower converges, and that number is its height. If they do not, the tower has no value at all. So the square root of 2 behaves beautifully. It would be easy to assume every base does. It does not. Nudge the base up to 1.5, barely a tenth larger, and run the exact same process, 1.5. Then 1.5 raise to that, which is about 1.84. Raise 1.5 to that, about 2.1. So far it looks a lot like before, climbing gently. But keep going, and the steps stop shrinking. They start to grow. 2.35, 2.6, 2.9, 3.6, 4.4, then almost 6, then 11, then 86, and now the tower is doubling and redoubling with every floor, sprinting toward infinity with no ceiling anywhere. Same rule, same infinite stack, 2 completely different fates. One base lands softly on a finite number. A base only a hair larger explodes, somewhere between the square root of 2, which is about 1.414, and 1.5, there has to be a dividing line, a single base where the gentle landing turns into a runaway. Finding that exact boundary is the whole game, and the way in is to ask what a well-behaved tower actually has to satisfy. Here is the one clever observation that cracks the whole problem open. Suppose a tower does settle down, and call its final height y. Now look at the tower and notice something about its own structure. Sitting directly above the ground floor is another infinite tower of the exact same base, identical to the whole thing. An infinite tower has an infinite tower inside it. So if the entire tower equals y, then the part above the first floor also equals y, which means the whole tower is just the base raised to y. In one line, y equals the base raised to the power y. The height appears on both sides. The tower eats its own tail. That little equation is the key to everything. It ties the base and the final height together with an iron rule. Now do one small algebraic flip. We would like to know, for a chosen height y, which base produces it. Take the equation and solve it for the base instead of the height. The base is y raised to the power 1 over y. So every achievable height y comes from one specific base, and that base is y to the 1 over y. This flipped form is the one that gives up all its secrets, because now we can simply sweep through every possible height and watch which base it demands. Plot that relationship. Height across the bottom, the base it requires up the side, and trace the curve of the base equal to y raised to 1 over y. Start low. A tiny height needs a base near 1. As the height rises through 1, 2, and beyond, the base it requires rises too at first. The curve climbs, but it does not climb forever. It bends over, reaches a single high point, and then turns back down and falls away toward 1 again for very tall heights. That is the entire shape of the thing, up to one summit, then down. And everything depends on that summit, because the base at the top of the curve is the largest base the whole family can ever produce. The summit sits exactly at height y equal to e, that famous constant 2.718, the base of the natural logarithm. And the base at that summit is e raised to the power 1 over e. Work it out and it is 1.4446, and change. That number is the answer. It is the tallest base the tower can survive, and the height it reaches there is e itself. Ask for any base below 1.4446, and the curve offers you a height. Ask for a base even a whisker above it, and the curve has nothing to give. There is no height whose equation that base can satisfy, so the tower cannot settle, and it does the only other thing it can. It runs away. That single value, e to the 1 over e, is the cliff edge of the whole subject, and Euler is the one who pinned it down. Now go back and settle the small mystery we left behind, because the curve just answered it. Why did the square root of 2 land on 2 and not somewhere else? Look at where the base 1.414 meets the curve. A base below the summit does not cross the curve once. It crosses it twice, once on the way up and once on the way down. For the square root of 2, those two crossings sit at height 2 and at height 4. Check it directly. 2 raised to the power 1/2 is the square root of 2, and 4 raised to the power 1/4 is also the square root of 2. Both heights obey the self-eating equation perfectly. So the tower has two candidate answers, and it picks one of them. It always picks 2. The tiebreaker is stability, and it is the same idea that decides whether a marble rests in a bowl or balances on a dome. The lower crossing, at height 2, is a bowl. Nudge the tower a little off of 2, and the process pulls it right back. The upper crossing, at height 4, is a dome. The tiniest push and the process rolls away from it and never returns. You can even measure the steepness that separates them. At the height of 2, the pullback factor is about 0.69, comfortably less than 1, so it is stable. At the height of 4, it is about 1.39, bigger than 1, so it is unstable. The tower, grown patiently from the ground, always rolls into the bowl, so the square root of 2 gives 2, and the 4 just sits there, real but forever out of reach. With the summit understood, walk the base slowly up toward it and watch the height respond, because the approach has its own drama. A base of 1.2 settles at about 1.26. A base of 1.3 settles at about 1.47. Push to 1.4 and the height jumps to about 1.89. The square root of 2, 1.414, gives 2, as we know. 1.44, just shy of the summit, reaches all the way up to about 2.39. And exactly at the summit, at 1.4446, the height arrives at e, 2.718. As the base creeps the last tiny distance to the cliff, the height it reaches climbs faster and faster, straining upward toward e. Then step over the edge by the smallest amount and it all falls apart. A base of 1.45 is past the summit, and its tower does not settle at a slightly higher number. It settles at nothing. It climbs and never stops, off to infinity, exactly like 1.5 did, only it takes a little longer to get going. There is no gentle transition, no base that reaches a height of say 5 or 10. The heights run smoothly up to e, and then the very next step is an infinite runaway. The whole rich range of finite towers is crammed into bases between 1 and that one cliff, and the height they cover runs only from 1 up to e, Beyond the cliff, there is only infinity. The tall side of the story is only half of it. Now shrink the base the other way, below 1, and a second, stranger edge appears. Bases between 0 and 1 behave at first just as nicely. A base of 1/2 gives a tower that settles at about 0.64. A base of 0.2 settles near 0.47. Smaller and smaller bases keep landing on smaller and smaller finite heights, all the way down until the base reaches about 0.066. That value is the second cliff, and it equals e raised to the power -e, the mirror image of the number on the tall side. There the tower settles on 1/e, about 0.37. And just past it, the tower does something it never did before. Drop the base to 0.06, a touch below the cliff, and the running values refuse to pick a single home. They start to swing. High, then low, then high, then low, forever, bouncing between two separate values, near 0.22 and near 0.54, and never choosing. The tower has not exploded, the way it did on the tall side. It has split. The even floors approach one value, and the odd floors approach a different one, and the structure oscillates between them for eternity. Because there is no single number the tower approaches, it has no value at all. This is the other way a tower can fail. Not by racing to infinity, but by never being able to make up its mind. So now the whole answer is in view, and it is beautifully tidy. An infinite power tower settles on a finite number when, and only when, its base lies in a single closed stretch. From e to the -e on the low end, about 0.066, up to e to the 1/e on the high end, about 1.4446. Inside that stretch, every base has a definite height, and those heights sweep from 1/e at the very bottom, through 1 in the middle, all the way up to e at the very top. Outside the stretch, on the high side, the tower runs away to infinity, and on the low side, it fractures into an endless oscillation. Two constants, e to the 1/e and e to the -e, fence in the entire world of infinite towers. Euler published this in 1778 in a paper on repeated exponentials. He is the one who saw that the summit of that curve had to sit at the height e, and that the base there, e to the 1/e, was the exact edge. What makes it so satisfying is how the two ends rhyme. The friendly constant e governs both cliffs. On the tall side, the boundary is e raised to 1/e, and the last finite height is e itself. On the short side, the boundary is e raised to -e, and the last finite height is 1/e. The same number, standing guard at both ends of the only interval where these towers are allowed to exist. That is the complete classical answer, and for a long time, it was the end of the story. It is not the end anymore. Tetration, this fourth operation, is still the least understood of the basic ones, and the reason is a question that sounds innocent. We know how to build a tower with 2 floors, or 3, or any whole number of floors. We even know, thanks to Euler, exactly which infinite towers make sense. But a tower with 2.5 floors has no obvious meaning at all. For adding and multiplying and powers, we long ago found smooth ways to fill in the fractions between the whole steps. For tetration, no one has found the single right way to do it. There are several competing extensions to fractional and even complex heights, and mathematicians still do not fully agree on which one deserves to be called the answer. So the tidy interval Euler handed us, that clean stretch from e to the -e up to e to the 1/e, is not a closed book. It is the solid ground at the base of a subject that still has open frontier just above it. The oldest questions in mathematics are usually the ones with the cleanest answers. This one has a clean answer for infinite towers and a wide open one for towers of fractional height, sitting right next to each other. If you take one thing away, let it be this. A structure can be infinitely tall and still weigh exactly 2, and whether it does comes down to a single number, 1.4446, that Euler found, and the rest of us are still building on. This was another one in the series. Stay for the next.